So it's my pleasure to talk at Hubert's birthday party. I've known Hubert for many decades. I don't want to specify how many. It has been always an interesting experience to talk to Hubert, to have discussions. It was always very original and unexpected angles. We don't always agree, not on physics, not on politics, not about life, but it's always interesting. So I hope to have many, many discussions. 60 is halfway in the Jewish tradition, so I wish you the second half will be as much fun as the first. I have an echo of my voice. Is it possible to?
Hello, Natan. It's Hubert. I just wanted to say we're here. I know you can't even see us. It's really sad.
Right.
But
okay.
Hello, and thank you for your nice wishes.
Hi, Hubert. So I'm going to talk about work done with my collaborators, Parmesh Paznuri, currently a student, Patrick Azaria, whom you must know, he's based in Paris, and Colin Rylands, a former student now at CISA. And I would like to talk about work that we have done recently about one-dimensional superconductors. So I'll talk about several topics, but here is a representation of the superconductor. It's one-dimensional, finite size. Sometimes we'll put fields at the edges, sometimes we'll put a Kondo impurity. And I want to discuss interesting effects that we are going to be able to calculate. So here's the plan of my talk. I'm going to talk about an intrinsic superconductor, namely one with not in mean field theory as one often discusses, but one where we have four fermion interactions, attractive interactions which lead to opening to a superconducting gap. And we are going to discuss first what happens with open boundary conditions on finite size. We are going to do the phase diagram. I'm going to show that there are several phases. There is the spin singlet superconductor and spin triplet superconductor with open boundary condition. I'll show that the spin triplet is topological. In other words, I'll show that zero energy boundary conditions induce a spin quarter zero energy modes, fractionalized modes at the edge. And I'll start with a quantum approach. Then I'll show that the same result can be obtained in another regime of the phase diagram by doing a semi-classical approach. Historically, it was the opposite way, but I'll present it this way. Then I want to talk, Then I'll talk about twisting the boundary condition. I will show that by twisting boundary condition, one can make the spin singlet superconductor topological. That is actually a very pretty point, particularly if we want to realize it in experiment. It's much easier to have a spin singlet superconductors. And it would be nice to make them topological, have Majorana excitations at the edge. Then I will have a dynamical boundary condition at the edge. I'll put here a Kondo impurity, and we will see that a lot of very nice physics occurs. Of course, the topic of Kondo and superconductivity goes back to the 70s, but I'll show that and a lot of work was done, but mainly mean field theory, and people very quickly identified what is called the shiba phase. I'll show that actually the shiba, and it was confused with the Kondo phase. I'll show that these are two different phases, and we identify that there are screened, unscreened phases, shiba intermediate phases, and so on and so forth, unlike the case where we don't have superconductivity, where we have only one phase, the Kondo phase. If time permits, I will also talk about similar effects that we found in twisted spin chains. We'll show that fractionalization again occurs at the edge. Okay, so there has been enormous amount of work since the fundamental ideas of Kitaev, who showed that Majorana occur at the edges of P-wave topological superconductors. This was shown in mean field theory, but always a problem arises. What happens if you have a really interacting theory, which is charge conserving, charge fluctuations? Are they going to wipe out those edge modes or not? And this question was raised by Kesselman, Berg, and Azaria, and answered nicely in mean field theory. I will address it first quantum mechanically, and then I will reproduce their argument. So here is the model. We have a right and left moving fermions carrying spin. This is left movers, right movers. Sorry, I don't know why it's moving. And the interaction is a four-spin interaction, a spin exchange interaction. So we have two coupling constant. One is the G parallel and one is the G perp. And we impose a open boundary condition. Open boundary condition means a left mover here becomes a right mover here becomes a left mover. And this is known as the U1 Turing model, or if G perp equals to G parallel, then the symmetry is increased to SU2, and it's called the Gros-Neveu model. So the phase diagram is very well known. Particularly, it has been much studied in the case of periodic boundary condition. So here is the phase diagram. We have the region. I will work in the regions A and A hat, and on the line here, which are the symmetry line, which are called the Gros-Neveu lines. And you see there is flow from weak coupling to strong coupling. And this is the range where this is the attractive coupling where superconductivity occurs. So there are exact solutions of this model known since the late 70s. And what people have worked a lot about this model. The phase here, the phase A, where G perp is positive, is the singlet, spin singlet superconductor. And when G perp is negative, it's the spin triplet. And the phases are named by the way the order parameter behaves, whether it's the order parameter of the singlet or the triplet, which one dominates in the long range behavior. And these two phases are related by a duality transformation, which maps the Hamiltonian from A to A dagger, namely G perp to G minus perp, but the boundary conditions break the duality, and it's very interesting to understand what happens to the mapping. So this model was also studied more recently with open boundary conditions, and the phase diagram was obtained using DMRG and semi-classical approach by the group Kesselman, Berg, and Azaria. And what I want to present is the Bethe-Ansatz solution that we recently obtained. So what I will show is that at the edges, there will be fractionally spin zero energy modes localized at the edges at both sides. And they are protected by this is an example of symmetry protected topological phase, and the symmetry that protects them, but which is fractionalized, is a spin flip symmetry tau that maps spin up to down, which again is violated by boundary conditions. Okay, so let me first present very quickly the solution. We can solve for all G perp and G parallel in the regions A and A hat, G gross Neveu and gross Neveu hat, which are the SU2 symmetry extensions of the U1 theory. And a solution proceeds as usual. We write down a beta ansatz, but this is now a beta ansatz on a finite length with finite boundary conditions. So for every k, we have also a minus k to take care of the reflections at the edges. So we have 2 to the n sets of momenta. This goes back to Godin. Sklianin formulated the method in a systematic way. And the amplitudes in each, so we partition configuration space according to all the orderings, and the orderings are related, the amplitudes are related by the S matrices, which are labeled with parameters F and eta, which are related through these relations to G parallel and G perp. And using the beta ansatz technology on open boundaries, we can obtain the solution. We find that the allowed Kj are given by an expression of this type, where theta is written down here, characterized by spin rapidities lambdas, lambda going from 1 to m being the integer that tells us what is the spin symmetry of the wave function. And the lambdas are solutions of a beta ansatz set of equations. You see here, this term here is due to the boundary term. So, and this term is the bulk term, and this is the interaction. The I alphas are integers. So the integer m determines the total spin. We had quantum numbers nj, which are integers, and quantum numbers I alpha are integers, and together they are the integers that characterize the many-body state, like in a hydrogen atom, N, L, and M are the quantum numbers that characterize the spin, the hydrogen wave function. Here we have an infinite set of integers that characterize the wave function. So the parameters U and F that appear, namely these are function of G perp and G parallel, are real, and they are sent to 0 if I want to take the SU2 limit with a ratio U over F equals to G, and G then determines the coupling constant. Now, if you notice in the boundary term, the chi here is a number which can be either 1 or 0. It is 1 in region A, namely in the SSS, in the singlet phase, and it is 0 in the triplet region. And of course, we solve the model in the universal, namely in the scaling limit, where we send the cutoff to infinity, the cutoff being the density of the electrons is holding fixed. So what I want now to show is that in the triplet phase, we have 4 zero energy modes with fractional spin as z. Namely, we'll have modes plus minus quarter on the left, plus minus quarter on the right. While in the singlet phase, we have none. So the triplet phase is a topological phase according to the conventional classification. So to do so, we solve the beta ansatz, and we find indeed a unique ground state. As z in the phase SSS is 0. But in the triplet phase, we find several phases, several solutions of the beta ansatz, all with 0 energy. To begin with, we find a two states with plus minus half, and where all lambdas are real. Then turns out we can also add a boundary state, lambda equals to plus minus I over 2, and we found now another state with SZ being 0, unlike here where it's 1. It involves charging energy because we change the number of particles, but the charging energy is of the order 1 over L and goes to 0 in the infinite volume limit. So we have then the states half, minus half, 0. Now, are there any more states? This is a question you always have to address, because when you have symmetry, beta ansatz gives you highest weight, and you have to worry about that. So the symmetry that is very interesting here is the flip symmetry, tau, a Z2 symmetry. We flip again, we are back. So in order to make sure that we don't have other symmetry, we have to, that we have all states. We want to break the symmetry slightly. We do that by twisting the edge, by introducing a twist matrix which of this form for very small epsilon. Turns out that the Hamiltonian is still integrable in the presence of twisted boundary conditions. But now the boundary term, which was 2 theta, goes into sum of 2 different thetas. So we have now a theta of the same form and a theta which is twisted by the amount that I have here, where epsilon prime is given by 2 epsilon over u, and again, epsilon prime is held fixed in the scaling limit. And we find, still in the singlet phase, we have only one state, no boundary solution, while in the triplet phase, we find a new solution. We find that there is another string present, lambda, of the form plus minus I1 minus epsilon prime over 2. So in sum, we obtain 2 singlets and 2 singlets, 0 and epsilon prime, and 2 spin plus minus half. And we are going to interpret this as being due to the fractional spin edges state. So we claim that we have quantum kinks at the edges, plus minus quarter on the left edge, plus minus quarter on the right edge, and with these eigenvalues. So that the 2 states with SZ equals to 0 are quarter on the right, minus quarter on the left, minus quarter on the right, quarter on the left, and we have then the spin half. The 2 states are quarter, quarter, minus quarter, minus quarter. We can rewrite all of this very nicely in Majorana language, but let me skip that and move to the semi-classical argument. Semi-classically, it's convenient to change to bosonic language by a standard bosonization formula of the fermion, which allows us to express the Hamiltonian in terms of 2 fields, phi charge, phi spin, and their conjugates theta s and theta c, which decouple. So charge and spin decouple. For weak coupling, so the coupling constants beta and m naught and us are all related to the original coupling constant. And in particular, if G parallel and G perp are small, which is the place that we are interested in, where quantum fluctuations are large, then we see that beta square over 8 pi has this form, so that beta square is, if we want, for example, beta square to be 0, that means a G parallel has to be large. And we can express now the total number of electron by an integral over phi c, and the total spin by an integral over phi s. And what is very important is that the boundary conditions now can be expressed in terms separately of phi of the charge phase and of the spin phase. And we have, let's say, phi s on the left is 0, while phi, the spin field on the right, is 4 pi over beta sz. And very nice work, I should mention, was done on, of course, on the Sine-Gordon with a different type of boundary condition, the Dirichlet boundary condition by SALEUR and collaborators. So now what we see here is a way that we can take now semi-classical limit for the model when beta goes to 0, holding the mass fixed. But that corresponds to G parallel very large. In other words, we are in this part of the phase diagram, while we are really interested in the dynamics of the strongly fluctuating quantum behavior. But it turns out that we can obtain very nice results in this regime. Now, the way we do it is we identify what are the dominant field configurations in the case for the bulk. Phi n, phi Sn is of the, to minimize the cosine term, phi s has to lie in a value of n over 2 pi over beta when chi is positive, while when chi is negative, namely chi is negative, we are in the A bar. In the A hat phase, it has to be of n of the form n plus half over 2. So now we want to match together the boundary condition and the bulk. So there is a mismatch in the case where chi is negative, namely in the topological phase, because you see the green line here describes where the value of phi is in the bulk, but the boundary condition locks us to this value to either 0 up to 2 pi over beta. So you see that there is a region of mismatch on the left and the mismatch of the right. So we get 4 types of excitation. We can go up and down, up and up, down and down, down and up. And when you calculate what is the spin content of each kink here, you find you do the integral over the spin density and you get plus minus a quarter, fitting what we get from the quantum results. And we get then again 4 states which are degenerate up to 1 over L. So what we showed so far is that the singlet phase is trivial while the triplet phase is topological. And the 2 phases cannot be connected adiabatically while maintaining the Z2 symmetry. We have to close the gap when G perp is 0. Now, we want to generalize it, in particular, because we want it's much easier to realize singlet superconductivity. So what I want to show now is that topological nature of the phase is really not only determined by the interaction in the bulk, but by the interplay of the bulk with the edges. So let us now twist both edges on the right and on the left. So we have now a twist matrix here, a twist matrix here, where the twist matrices are written explicitly in integrability. And these twists, while they look mathematical, they are actually can be shown to be obtained by imposing external magnetic field. So they can be realized in nature. So what happens now is that the Z2 symmetry is in generally broken. So the Z2, what does the Z2 symmetry do? B now goes to sigma xb, acting on the twist matrix, which means that epsilon goes to minus epsilon. So the Z2 maps an epsilon on the left to minus epsilon on the left, epsilon on the right to minus epsilon on the right. So that means that there are only two values that are consistent with the Z2 symmetry. These two values are either epsilon equals to 0 or epsilon equals to pi over 2. The epsilon equals to 0 is just the open boundary condition, which I discussed earlier. And the pi over 2 invariant boundary condition turns out to be I sigma z, and it's a twisted boundary condition. So we have an open boundary condition and twist open boundary conditions. And what we are going now to do is to measure the twist away from those invariant values. So these two invariant values give us 4 or 0 degenerate edge modes. While twisting away, there are deviations from the fixed points, and then they are no longer symmetry protected, and the local modes are going to acquire a mass gap. And we are going to have then what is called mid-gap states. Now, let me first give a quick argument just based on topology. We have a duality symmetry that maps the model from G to G, from G perp to minus G perp, and it maps the boundary to minus boundary. So in particular, the open boundary condition is mapped to open boundary condition hat, but both models have, since the duality is a symmetry, they have the same spectrum, and therefore we find that the singlet phase with twisted boundary condition will also become topological and exhibit Majorana zero energy modes, while the triplet phase with this twisted boundary condition becomes trivial with no zero energy modes. While now, if you want to move away from the fixed point, then labeling the deviations by an invariant variable epsilon minus epsilon star over 2u, this variable is held fixed in the limit, in the scaling limit. We can label we obtain a very rich phase diagram. So around the trivial region, we see that deviations are not going to change the state. We are going to remain with a singlet, namely Sz is equal to 0, even when we are twisting away from the value 0, 0. But when we twist away from the topological, namely from the twisted open boundary condition pi 2 over 2, we are going to have a very rich phase diagram. We're going to have mid-gap states. The zero modes that were degenerate now acquire a finite mass, but the finite mass that they find gap is going to be below the mass gap. So they are now mid-gap states. And we can see that there are different number of mid-gap depending on the regions. So here we have a phase diagram labeled by epsilon prime r, epsilon prime l. 0 means that they are untwisted. Around 0 up to 1 and minus 1, the regions A are going to be mid-gap states with three mid-gaps, while if we keep twisting more to B, we are going to lose one mid-gap, which is going to leak into the bulk, and regions C, again, we are going to lose more mid-gaps, which are going to go into the bulk. So let me quickly describe, for example, what happens in region A. Now the epsilon primes are smaller than 1. So what we are getting now is 4 states. Again, when epsilon prime goes to 0, they revert to the twisted open boundary degenerate states. But when the twist angle is different from 0, then we compute and find that they acquire a mass gap, which is given by this expression, m left or m right is m, the superconducting mass gap, times sinus pi over 2 epsilon prime L or R. And then the spectrum in A1, namely here, is going to be epsilon minus half, which is the ground state, and then the other values are epsilon minus half plus ml, or mr, or ml plus mr. And they are going to be the fermion parity, namely P, which is minus 1 to the L, it becomes minus 1 plus 1 plus 1 minus 1. So the state is built with real lambdas, beginning from the up reference state. The two singlets are obtained by adding boundary bound states. That was also done earlier by Skorik and SALEUR. And the boundary states are given here by 1 minus epsilon prime over 2 and plus minus on the right and on the left. And however, when epsilon prime is equal to 1, as you can see here, m left, m right becomes equals to m, and the mid gap becomes part of the bulk excitations. And we have other regions, Bj, and we have a lot of fun by discussing phase transition from region B1 or B5, namely phase transition here to here or here to here, depending how you play with the external parameters. And you can write down an effective Hamiltonian that describes also these dynamics. You can introduce fermionic operators. You see, because we have mid-gap states, when we add a fermion to the system, it prefers to go to the edges. And then we can talk about a psi dagger on the left, psi dagger, let's say, on the right. And they are going to generate, by acting on the ground state, a singlet phase on the right or on the left. Or if we add at both sides, we are going to get an excited spin half excitations. And we can introduce fermionic operators, A, left, and right, that do this job and create all those states and work directly with an effective Hamiltonian that creates all the physics at the edges. Okay, let me switch to another topic. Let me now, instead of having here a fixed boundary condition, let me have here a dynamic variable, namely a spin. So now what we found, we can solve the superconductor with a Kondo impurity attached at the edge. So we have two couplings, and we can solve the model with two independent couplings. So G is again the SU2 invariant superconductor. G perp equals to G parallel equals to G. And J describes the hopping from left, from the edge to the impurity and a spin flip. So what we show is that we have quite a rich phase diagram that we obtain. So in the superconductor, a gap opens as usual, delta equals to 2, D is the cutoff, e to the minus pi over G, that is the superconducting gap. If we hold G fixed, then as a function of J, J can be large or small compared to G. We are going to get various phases, which we are going to label by an RG invariant combination D, which is square root of 1 over 2g squared minus 1 over 2g times j minus 1. This is a solution of an RG equation where both g and j may evolve under changing the cutoff, but leaving this combination invariant. So what we get is various regimes. There is the Kondo regime, where the coupling to the impurity is larger than the coupling in the superconductor. We get a many-body screening of the impurity by many-body screening by spin fluctuations, and with a Kondo-generated scale, Tk is the delta times E pi over d. This is d, which takes the form, the conventional expression d equals to minus pi over 2j when j is very large compared to g. Then there is the shiba mid-gap phase, where j is of order g. This has been studied since the 70s, and we feel that people have been a little bit confused about it. What you find here, there is no scale generated. You have local spin accumulation, namely bound states at the impurity site, which screen the impurity, but this is not a genuine Kondo phase, although people identify it as such. The screening is local by a bound state on the impurity, not a many-body screening.
Sorry,
and then
Natan.
we have...
Hello, just
Yes.
to tell you that you are running out of time almost.
Okay.
So you have a couple of minutes if you can. Thank you.
Okay. So here is the phase diagram with all behaviors. Here we have the Kondo regime. Now I'm weakening the coupling, and I go to an intermediate phase, Shiba phase, where we have only local spin accumulations on the site of the impurity. Here it's the unscreened phase. Okay, I'll skip that. Diagonalization, calculation of density of states, magnetization. A very quick statement about the Heisenberg spin chain. Again, you can solve it with boundary condition. This has been done long ago. And you can study, again, as we studied the twisted superconductor, getting various phases, various bound states, various mid-gap states. And again, a very rich phase diagram. So let me conclude. So we studied the one-dimensional intrinsic charge-conserving superconductor on the open line with open boundary condition. We identified topological phase with fractionalized spin zero energy modes. We applied twisted boundary conditions, and we identified many different mid-gap phases, and we showed that even the spin singlet can be made topological. We solved the model with now a Kondo impurity attached at the end, again, quite a rich phase diagram. And we also showed that such fractionalization would occur for edge modes in the Heisenberg spin chain. And of course, there is a lot of direction to generalize. We can couple several wires at the edges. We can generalize, couple several superconducting modes at the dot, get a multi-channel superconductor Kondo effect, generalized to SUN, get parafermionic edge modes, and so on. There is a long list that we are working on. So happy birthday, Hubert, and thank you very much.
Thank you. Are there any questions from the audience here?
So, yeah, I have plenty of questions, but I'll ask only one because we're running, alas, late. But when you find your excitations Sg equals plus or minus a quarter, my feeling is you haven't really shown that they're localized at the edge. You would need to look at the wave function. And did I understand? I mean, you get this by counting, but you haven't yet understood the profile near the edge. Is that correct?
That is correct. We understand it semi-classically.
Yeah, sure. But in the beta ansatz, in the beta ansatz, of course, you ask the right question, which is very difficult. What you want me is to calculate the wave function at the edges. Yeah.
But what the argument is that are zero energy modes which cannot exist in the bulk. They can only exist at the edges. So that is the argument.
Okay.
Combined with semi-classical calculation.
Yeah. Okay.
But the full real argument would be to do what you have done at the edge of a magnet to try to understand the wave function at the edge. That's very difficult. But I don't think that there is an issue that the modes are at the edges.
Yeah, I mean, I was wondering about the interaction between the two edges for short chains, right? They're only decoupled for very large chains.
If they are, they are decoupled for large, L goes to infinity, in which case also the charging energy goes to zero. Otherwise, we have a much more complicated system.
I see. Another question I had, back in the 90s, people like André Leclerc and Robert Koenig studied what they called the massive Kondo model, which was basically a massive sine-Gordon theory with a Kondo spin at one point. Would that be the bosonized version of your impurity in the 1D superconductor?
That could be. I mean, if you bosonize the fermionic, the superconductor, it is indeed a sine-Gordon, a charged sine-Gordon, but I have to study. I'm not sure I know this work. So.
Okay. Well, thank you, Natan. See you soon, I hope.
Yes.
Thank you. I think there are not more questions, and we're a little bit late. So thanks again, and see you soon.
Thank you.
Bye.
Bye-bye.